So critical points, first derivative equal to 0, points of inflection, second derivative equal to 0. You've got about 2 minutes at your table. Come to consensus on the answer for this multiple choice, the no calculator. Is this a first derivative test or a second derivative test? Okay, Noah says it's a second derivative test.
Yeah, I already have one.
No, you can't hit it back.
Oh, yeah.
Okay.
I didn't get to it much.
So come to consensus. Can anyone give us some tips as to how to rewrite, maybe how you want to rewrite this to make taking derivatives easier? How do you want to rewrite this function to take the derivative more easily?
I write it as x to the -2 minus x to the -3.
Yeah, now we can do our power rule. We've got negative powers, but that's okay. I'm just going to check to see the consensus that you've reached. Sure. Okay. So. Yeah, it's definitely, anytime you see a multiple choice question in the anywhere from 1 to 28, that's a no calculator, so try to do it without your calculator. Anytime you see a multiple choice question in the 70s, 80s, and 90s, that's a calculator question. Definitely a no calc. It's not that I would rip the calculator out of your hand or anything, but that looks like a good second derivative. That looks like a good second derivative. Set it equal to 0. After you get your second derivative and you set it equal to 0, then you might want to put the x's back down in the denominator. It might help you solve it algebraically. Okay, so most people are getting this as their second derivative. Actually, all of you are getting that as your second derivative, which is correct. And I see people are setting that equal to 0, which is also correct. So if you've gotten that far, you've done the calculus. And now they do expect you to do a little bit of algebra. So bring one of those fractions to the other side, or try to factor out. I'm going to use the factoring method as we go through this, and explain why either works just fine. Consensus here? Just checking to see if we are in agreement. Have we reached an agreement here at this table? Yeah.
Oh, three.
Are we in agreement, right?
Yeah.
Fractions are 0 and the tops are 0. And then we'll talk a little bit about the bottom being 0.
No,
I reached consensus here.
oh,
No. Okay. You factor out 6. So I agree. We're going to factor out 6. Yeah, so that is, we reach consensus here. I know. That is can't help with that. So. Consensus over here? I'm frozen? Alrighty. So consensus is?
2.
You're right. Okay. So answer is 2. So how do we solve this? That's kind of the big question. What's my highest power of x? X to the 5th, right? So I'm going to multiply both sides by x to the 5th. And I'm going to get 6x minus 12 equals 0, right? Because x to the 5th times 0 is still x to the 5th. Where does that make x? Makes x equal to 2. Okay? Now, I saw a lot of people doing this, which is also a great way to solve it. Right? And so really when we solve it this way, I saw a group doing this, which is great. Getting in the habit of factoring. Right? So if we factor out a 6x to the 4th, we're left with that solution. What does this solution imply? There's two zeros, right? One is what? What makes this 0? 0. And then this one is, yeah, that's the answer we were getting over here. And they're both an option here. So how can we be smart enough? The nice thing is not many people actually follow this path. That's nice because it doesn't lead you down towards the wrong answer. Most people did this sort of thing. How do we stay away from this answer? It's enticing. We love 0. Why is it not an appropriate answer? Yeah.
Would it be if you put 0 into the original equation, it would be undefined?
Does that make sense? Putting 0 in here, our function isn't defined there. What about putting 0 in for the derivative?
Fine.
Same problem. Our derivative isn't defined. Okay, if our function and our derivative aren't defined, this can't possibly be an answer. Does that make sense? So we have to check that scenario too. Okay, so this whole chapter has been about what? What's the title of this chapter? Whole thing. We started way out back in section 4.1 a week or two ago or more.
Extreme values of function.
Okay. Nobody knows the title of this chapter? What's the title of this chapter?
Applications of derivatives.
Applications of derivatives. Okay, so we've spent a good part of the chapter talking about what happens when we take the first and the second derivative and what characteristics that gets us on a graph. And so today we're going to really pay special attention to that first derivative test. So if we've got a function, maybe something that's nice and polynomial-like, and we do the first derivative test, the first derivative test is going to find what? Characteristics. Zeros? Okay, what do you mean by zeros? Okay, hills and valleys. So when you say zeros, if we're finding valleys and hills, what is equal to 0? The derivative, right? The zeros of the function would be these points. Okay, so we are finding that these points here where the derivative is 0, those are called critical points. Okay, this is also a critical point. This plateau is also a critical point. But the hills and valleys have really nice applications. And that's what really we're going to focus on in this section. So we're going to focus on things like, what is the maximum volume of a box made from a piece of cardboard? Okay, so if we pose that question, going back to this graph, what am I asking you to find? If I'm asking you to find how much a box could hold. A max, which would be, what do we call this point up here? What term did you give that just a few minutes ago? It's not really a mathy term. Yeah, it's a hill. Okay? And if we ask questions like, how can you minimize the material needed to make a can? That's asking you to find what on the graph? Minimizing something graphically would be looking for what? That minimum value or that valley. Okay, so if we look at these practical applications, what is the maximum volume of a box made from a piece of cardboard? Why would that be important?
So you can get as much into a box as you could using the same amount of cardboard as you could.
Yeah, so we can fill the box with as much as possible. Minimizing the material needed to make a can. Why is that important?
Save.
It saves money. How about the rectangle with the largest area that you can inscribe in a circle? A little tougher to find. a practical application for that one. We're going to do it, but it's a little tougher to find. How about what production level maximizes profits?
Make more money.
Make more money, right? Our entire capitalist structure is based on that problem alone. So we have some strategies for solving these problems. I love the first strategy, understand the problem. I think if we could just understand all the problems, we'd have a really easy time solving things. But really what it means is that we need to be able to kind of read critically and identify the information and sort it into what I need to find, what I have, that sort of stuff. We need to develop a model. Okay, so models involve pictures, graphs. We need to be able to represent quantities in terms of equations and that information. We need to be able to graph it. And we need to be able to really solve this mathematically. So we're gonna have to look at the tests. So we're gonna have to look at these derivative tests. We're gonna have to be able to solve things mathematically using algebra. So really when we're talking about solving these problems, we're talking about really two methods. A being a graphical method and B being an analytical method. In other words, a method using algebra and our calculus. And then we're going to have to be able to give this some meaning and draw a conclusion from our calculations. So we're going to take that box example and look at that first. Okay, cardboard is typically purchased in pre-cut standard sizes. So a place like Amazon gets cardboard to make boxes. They literally get these flat sheets of cardboard that they got to stamp boxes out of. Okay, it's used to ship just about everything. For Amazon to use as little cardboard as possible, but be able to ship as much as possible. The ideal situation would be able to make a box using just one piece of cardboard. And we want what for the volume? We want to do what with the volume if we're going to make this box?
Make it as close to the volume that you need.
Okay. What if we want to ship as much as possible?
Make it as big as you can.
Okay, so we want to maximize the volume. So that's part of that first step is just being able to identify, am I minimizing or am I maximizing? Am I going to look for a hill or a valley? Okay. So we're going to simplify this just a little bit. If we look at these Amazon boxes here, have you ever taken apart a box and unfolded it flat?
Yeah.
Okay. Does it pretty much make a rectangle? It does. But that box has several cuts in it and several folds in it. And that's a little more complicated than we're ready to deal with mathematically. So we're going to simplify this just a little bit. And we're going to make a Christmas box. You've ever seen the boxes you put like sweaters and shirts in, right? They got a bottom and a top, and they're separate, right? And the bottom is literally just a flat piece of cardboard that's bent up like that and taped on the corners. We're going to make that kind of box. Okay? So if we take a look at this box, really what we have is a flat piece of cardboard, and then we cut the corners out so that we can bend those corners up. So we end up bending up those little tabs. So we end up bending up those little tabs to make our box. Okay? And so what we're going to do is we're going to make a box out of a 20 by 25 inch sheet of cardboard. So this cardboard, when it was originally shipped flat, was 20 inches by 25 inches. And if we fold this up, then we are making a cardboard whose bottom looks like that. Does that make sense? Then we're going to fold up the sides. So these are sides. and we're gonna fold those up. If I cut off a little bit, a little corner, and let's just label that cut X, how big does that cut have to be in order to make the biggest volume possible? So what are we trying to maximize? Volume. What is the constant? Shoot. There we go. So if you look at that, second question, what is the constant that we need to relate to the above quantity? So in other words, what about this problem that Amazon has is going to stay the same? Okay, I agree. However much they cut out is going to dictate how tall this box is. What is the thing that they can't control? What is the thing that has to remain the same? The size of the cardboard. Okay? And so we know we want to maximize volume. What's our volume equation?
Standard.
How do we find the volume of a box? Length times width times height, exactly. Okay, and so once we fold up this box here, we have a definite length for our box. We have a definite width for our box, and we have a definite height for our box. Okay? So if we cut up these corners X's, and this is 25 inches, then what is this remaining part here? If we cut off a distance X and cut off a distance X, the bottom of the box then becomes how long? Exactly, this becomes 25 minus 2x. And what about the width of the box here? That becomes how much? That becomes 20 minus 2x. So now we have, in terms of the dimensions of our box, the length, the width, and the height of our box, we have expressions that we can now put in. So our length is 25 minus 2x, our width is 20 minus 2x, and our height is x. And so we want to maximize that function. And so we're going to look at this two different ways. We're going to look at this graphically, and we're going to look at this analytically. Okay? So let's look at this graphically first. Go ahead and graph that function in your graphing calculator. Put that in Y1. And the nice thing is, graphically, we don't have to do anything to change that. Just put it in there in that factored form. And let's take a look at what we have there. Okay. Let me see your white. Yep, that looks good. Okay, so we definitely have a picture problem, right? So how are we going to fix that picture problem? Yeah, in fact, I would just do like a zoom out or something, try to get a better picture. But you can play around with the window that way too. What does that graph look like? Awesome, good window. Good window, yeah, that's a good window. So if you're seeing just two really big vertical lines or something that looks like a parabola, zoom out. Yep. Do a window. Actually, I do a zoom. I said that wrong. Go next to window and then just do zoom out. And then just go ahead and enter. Better? Okay, you go ahead and zoom out again. Okay, so I would go ahead and change the scale and go from like 1 to 30. The X, yeah. Okay, so we're starting to see it. So maybe you get that top value. What the top value, so Y max. Where's your top still cut off? Okay, you're getting closer. Yep. Well, think about what we're multiplying together, right? I mean, if we look at that function, 25 times 20 is 500. So we're talking about something that is at least 500. Yay, there we go. That looks all of it. Now, so if we look at this, right, we've got these three things multiplied together. What degree polynomial is this? What's the degree on the power? What's the biggest power? A third degree polynomial, right? So we should have something that looks like up, or down, up, down. Okay, so we should have something, whoops, that looks like this. And so we just need to talk about the characteristics, as we've been doing all chapter long, that we see here. Where's our maximum volume going to be?
Well, there's two different ones.
Are there two different maximums?
Well, there's an infinite.
Okay, so how many want to create a box with infinite volume? Ah, you would be Amazon's favorite person, I think. Realistically speaking, we have one maximum volume and it's located there. Are there parts of this function that just don't make physical sense? Where are those parts of that function?
Negative
Negative
volume.
volume doesn't make sense.
Infinite volume doesn't make sense.
Infinite volume doesn't make sense. So those are all not possible. So that being the case, what is this point right here? How much volume do we have down there?
0.
0. What is my x value at that location? My x value is 10. So think about the value 10 being put into this expression. What happens? This, yeah, the 20 minus 2x becomes 0. Which means if I have an x of 10, I'm cutting a notch here that's 10 wide, but my cardboard is only 20 wide to begin with. So if I cut 10 out of each side, I've just cut all the way to the middle. So that's not physically possible. We don't make a box at that point. Any other location, we make a box. Okay? So in your calculator, under Calc Max, we should be able to get the answer to our question. What is our maximum value? No calculations necessary. So Calc Max, it's going to ask you for a left bound and a right bound probably. And what is your maximum?
820.5.
820? 825?
No, 820.5.
Oh, 820.5.
And that's at 3.6.
And 3.68. Okay. So if I want to maximize my volume of my box, I'm going to be cutting out squares from the corners that I have 3.68 inches on its side. And then I'm going to start folding those tabs up. And that will give me my maximum volume. How are we doing? So what does this look like analytically? Because what will happen is you'll have these type of problems on the calculator part and the no calculator part. This will be a calculator question. But what is the process? What is the process to solve this analytically?
Take the first derivative and set it equal to 0.
Okay, so take the first derivative, set it equal to 0. How do you want to take the derivative of that?
Yeah, distribute.
Yeah, I would definitely FOIL that out. So if we FOIL this out, what do we get? 25 times 20 is how much?
5.
Okay, so at your table, go ahead and FOIL that out. Just go ahead and FOIL it. We'll take care of the derivative in a sec. Good. You are having bad iPad luck lately. Good question. If we want to find that max, is that max a critical point or a point of inflection? Points of inflections changes, our smiles and frowns change. But we're still on a frown, right? We're at a frown on one side, we got a frown on the other side. So it's not, so it's got to be critical point. Yeah, mins and maxes are critical points. Inflections change from frowns to smiles. And we change from a frown to a smile kind of halfway between those mins and maxes. All right, looks like some good foiling. What do we have here? What's my function?
4x squared.
Okay. I agree. Okay, so there's our function. We've got to take now what? We're going after the maximum value. Is that a critical point or is that a point of inflection?
Critical point.
That's a critical point. So we need what derivative?
0. Oh, first derivative.
First derivative and set it equal to 0. So our first derivative is what?
12x squared minus 90x. Oh, wait, 180x.
Good catch.
Plus 500.
Good catch. And I forgot to write an x there. Sorry about that. And that equals 0. Can we factor this? It's not easily factorable. In fact, at this point, it's a quadratic formula. And this is what I wanted to point out. This is why we kind of solved it anyway. Okay. At this point, we can't factor out a 12 because 12 doesn't get factored out of 500. We'd have to use a quadratic formula College Board is not gonna make you do the quadratic formula. They're just not, it's algebra, it's not calculus. They don't like to make you do a lot of algebra. They make you do a little bit, but they don't want you to do that kind of stuff. So this is definitely, with these numbers, this problem would definitely be a calculator problem. You'd find it on the calculator part of the test. If they wanted you to do a problem like this on a no calculator part, they would give you special numbers that were factorable so you could factor this. Okay? And then once you factored it, you're going to get a min and a max, right? So you're going to have to be able to pick which one is your actual physical value. Okay? So just to go through a full analytical solution, I want to talk about making a soup can. So slight career change. We're no longer working at Amazon. We're working at Campbell's. Okay? And Campbell's soup cans are made out of steel. Okay? And we know we use steel cans a lot, right? For anything we want to keep for some period of time. So fruits, vegetables, soups, sauces, anything. Okay? So there's a lot of reasons why we would want to minimize the material used here. Some of them are listed there. Obviously, Campbell's Soup wants to minimize material because what does that do for their company?
Saves money.
Saves some
and
money.
Makes them look green.
Makes them look green. Okay? If we're not an average recycler, we certainly want to have something where we're throwing away something that has as minimal material as possible. So we are definitely trying to minimize the amount of material used here. What physical quantity does that refer to? When we're talking about the amount of steel we need, that's around the outside of that can, right? So that is definitely what Noah said. This is definitely a surface area question. College Board will expect you to know the surface area of cylinders and cones and prisms, like boxes and stuff, and volume, okay? What's the constant that we need to be able to relate to the above quantity? In other words, what's not going to change? Campbell's still has to do what with every can of soup?
Make a certain volume.
They have to make it a certain volume, right? They've got these machines that spit out 10.75 ounces of soup all the time, every time a can passes. We better have a can that can hold that much. So we need to make sure that we satisfy the volume constraint. In this question, the volume constraint is 318 cubic centimeters. That's about 10.75 ounces. Okay? So, what is the surface area equation for a cylinder?
Height times plus the
Bless you.
pi r squared.
Yeah, that's really close. The can has a top and a bottom.
Oh, 2
What's-
pi r squared.
What's the area of circles? Area of circles is pi r squared, and we've got 2 of them. And then it has this curved surface, and if we cut that curved surface up its side and flatten it, it becomes a rectangle. It's got a height, h, and this length was wrapped around the can, right? That's where we cut it from. And so this length is 2 times pi times r. So this rectangle is this times that. We have how many of those rectangles? Just one of them. 2 pi RH. Okay? So there is what we need to minimize. We need to minimize that. But we also have a constraint. Our constraint is our volume. How do we find the volume of a cylinder?
The height times the base.
Yeah, the height times the area, the big B was the area of the base, remember? This is back in the day when you had geometry. And this is the base.
pi r squared.
That's a pi r squared. So the question is, and we know our constraint is volume. We know we need to keep our volume at 318. There's the constraint. And we know we need to minimize surface area. So we've got two variables, r and h. Which one do we want to keep and which one do we want to eliminate? And how do you know how to make that decision? Can you make a wrong decision here? I see some people. I see some people shaking their head no, and you can't make a wrong decision here. No matter what you decide to keep, you'll get the right answer. But there is one way to solve this that is easier than the other.
Well, if you keep the r, then
Okay. So Noah's saying keep the r. Okay. And really, what you want to look at is you want to look at this constraint here. Which variable is easy to solve for? H. Solve for the easiest variable in the constraint. So we're going to solve for h here, which means Noah's right. Once we solve for h and we put it in here, we're going to end up keeping the r. Does that make sense? Because the h is going to be gone. So what is this solve for h? What do we get here?
divide by pi r squared.
Okay, so we're going to put that in for h here. So we end up having 2 pi r squared plus 2 pi r times 318 over pi r squared. Okay, so we got some canceling we can do, right? What cancels out over here? Yep, a pi and an r on the top and one of the r's on the bottom. So we are left with,
318 times 2.
I agree, 2 pi r squared plus 636 over r. Okay. So if we look at that, taking the derivative of that is not too bad. But let's write this, let's get rid of this fraction. So we're going to write the surface area expression. What's 636 over r? How do we rewrite that?
636 times r doesn't make a
Okay. Now we can take its derivative. What's the derivative of the surface area? What's the derivative of 2 pi r squared?
4 pi r.
Okay, that's like saying what's the derivative of 3x squared? All right, bring down the 2, multiply it by the 3 to get a 6. So derivative of 6x. So all we're doing is bringing down the 2 and multiplying this out. So that's 4 pi r. And then what do we do here for the power rule?
You gotta subtract 360, 636, r to the negative 10.
Okay. And so we know that once we do the first derivative test, we found a critical point if we set that equal to 0. Okay. And as I was searching for boxes on Google, I came across that Amazon has a little box robot. He's pretty cute. He's playing hopscotch. Does all sorts of things. Google it. It's pretty funny. So if we look at this and we rewrite this without the negative exponent, then it's easier to solve. So go ahead and solve that algebraically and tell me what you come up with for the radius. When you put this, if you do calculate this in your calculator, have to divide by a 4 pi, which means you need some brackets in your calculator. So be careful about that when you calculate that. I agree. All of that. I agree with that number. I agree with that. You're gonna need an extra set of brackets right here because this is saying 636 divided by 4 times pi. Once you get those brackets in, you'll be good to go. 3 decimal places. 3 decimal places. When using a calculator, you want to round to 3 decimal places. That's College Board standard. 2 decimal places will get you a 1 point deduct. So we'll 4. You might take that back. 2 will. Did you suit? Okay, so we want to divide by 4 and 9, right? So we need brackets around there.
Yeah.
So we really want to divide this by about 12. Does that make sense? There we go. So 3 decimal places, the answer is 3.699 centimeters. Units are becoming more and more important as we talk about physical quantities. Okay? So if we would go home and measure a soup can, go to the top, measure its radius, we would find that it's not 3.699 centimeters. What did the soup company do? Did they make the can that holds? Did they minimize the surface area of that can? No, they didn't. So the question is why? When they had the opportunity to reduce material, why didn't they do it?
So they can put the label on, and then they can package.
So here's that, and well, we didn't get to it yet. If we would graph, totally forgot the graph. If we would graph this function, 2 pi r squared plus 636 over r. So if we're looking at a graphical solution here, 2 pi r squared plus 636 over r looks like this. There you go. So if you get a quick sketch, just a real general sketch on that, if that's what it looks like. So this minimum is about our 3.699 centimeters. Okay? That's what's going to minimize our steel. But in actuality, if you go back and if you go home and measure a soup can, you're not going to find that to be a case. You're actually going to find that the top of the soup can, and this is in inches, but the top of a soup can is closer to about the top of the soup can is just a little beyond. I guess this is a ratio, so that's not helping me. But
It says the excessive surface area is.
yeah. So the top of the soup can is actually a little smaller, and they make the can a little taller. Okay. And the question is why? Yeah, why don't they? Why this is where the optimum would be is if there's that 1-to-1 ratio of height to diameter. If we make it boxy, so why don't they minimize that? And I don't know what the answer is.
All the packaging, advertisement.
Okay, yeah, Noah's saying, well, they've got a label that's this tall. Maybe they don't want to redesign the label. How long have soup cans been around? A long time. Maybe they just made something that looked appealing and they just never changed it before they started, realizing that it could really affect profits. I don't know. But we notice soup cans, in fact, no can is really made that way. Tuna cans, which are really short, are at the other end of that optimal surface area, and soda cans are even less efficient use of material. So my guess is it has something to do with marketing. Just looks appealing. The ratios look good.
One for the soda can, you have to have it fit in your hand, so you can't just have a wide.
That's true. Yeah, you don't want a real wide soda can. So questions about that? Okay, so we've got some WebAssign. Tomorrow, since we got through everything today, tomorrow we've got just a few things to talk about, and it'll be by and large work day to crank out some optimization problems. Okay, so we've got our first assignment for tonight there.